In this video we're going to take a look at some of the Pwn challenges from the recent Angstrom 2021 CTF. Any scripts that I work on throughout this video will be uploaded to GitHub, so you can check the description for the link to that, and you can use the chapters feature if you want to skip to any particular challenge. But I hope you enjoy the video. If you do, drop a like and subscribe. Thanks. The first binary exploitation challenge is called secure login, and the description here tells us that we have a really secure login service. We're given a link to the binary and to the source code as well. So we want to have a look at the source code, try and identify the vulnerability. We'll test it out locally against this binary, and then once we've got it all working, we'll go to the actual binary on the shell server and try and get our flag. So I've already logged into the shell server and I have downloaded the files, so let's go and take a look at the source code. Before we jump into the source code, let's do some basic file checks as well. So we can run file on the login binary and see that it's a 64-bit LSB executable. It's not stripped, so if we didn't have access to source code, this would make it a little bit easier to reverse engineer and debug it because the symbols won't have been stripped. We can also run checksec as well to get an idea what protections have been enabled, and this can give us a good idea what the challenge is going to be about as well. So in this case we have stack canaries, so there's a good chance it's not going to be a buffer overflow. If it is a buffer overflow, then NX is also enabled, so we wouldn't be able to execute any code that we're able to inject onto the stack. And there's no pi, so each time the binary loads it'll have the same address. We wouldn't need to leak that. So there's no point in playing around with the binary. We might as well just go ahead and open up the source code first of all, see what's actually going on with it. So if we step through the code, we have a message saying welcome to the ultra secure login service, and then the generate password function is called. We have a note here as well, no way they can guess my password if it's random. So generate password is going to open the dev-urandom and is going to read in 128 bytes into the password char buffer, and then it's going to close the file. Next we have an input which is also 128 bytes, and we're asked to provide a password. Again, it'll take 128 bytes, there's no overflows or anything there, and then it's going to compare it's going to use string compare to compare the input that we've provided against the password which is read from dev-urandom. So in order for this condition to be true and for it to read in the flag, we would need to make sure that the 128 bytes that we enter matches the 128 random bytes from dev-urandom, which will obviously be random each time the program loads. So we could minimize this and run ltrace with login. We'll see here it's open dev-urandom, and you can see it's grabbed 128 random bytes, and then it's asking us to enter a password to say hello, and it's compared the hello that we've entered with the 128 random bytes and therefore has said that's wrong. So I've created a fake flag here, flag.txt, just so that whenever we actually meet this condition we'll be able to, well, we would still know anyway because we'd get the error saying missing flag.txt, but I've just put that there anyway so that it'll print it whenever we do match the condition. So what's the vulnerability here? Well, dev-urandom is going to bring back 128 random bytes. So each one of the bytes it returns is going to be a possible value between 0 and 255, so there's 256 possibilities. And one of those could be the null byte, so \x00, which we also know acts as a string terminator. So whenever the string compare occurs, if it reaches a null byte, then it's going to terminate that string, and essentially it'll be comparing everything up to the null byte with our password. So there's essentially a 1 in 256 chance of the first byte that dev-urandom retrieves being a null byte, and if it is, then it'll compare the null byte to our input. So if we can just input a null byte, that will essentially bypass the other 127 random bytes that would be returned. So we can essentially brute force this, right? So if we keep running the program, there's a 1 in 256 chance that we're actually going to get the flag. So we can run it, say, 1,000 times, and the chances are we'll get our flag. So let's test this out then. So I've already got a script here, which I just copied over the Pwn tools template, which I normally use on these videos, and what's it called here? Exploit.py. Let's open this up and take a look. So a lot of this is just kind of functions that were in the template. We don't need to worry about it. The only thing that we've actually added in is everything after the exploit goes here section. So we provide our exe. In this case, this is set to the remote server. So let's set this to the local login. I've just disabled login to make this a bit cleaner. So essentially we're looping 1,000 times here each time we're launching the program, and we're hoping that whenever the program launches and it generates this password, that the first byte that it gets back from dev-urandom is a null byte. If it is, then the null byte that we enter is going to match that comparison right here, and it's going to print our flag for us. And we've got a fake flag for testing locally. So let's run Python exploit, and you'll see it's saying enter the password. It's giving us our fake flag. If we wanted to, we could say io.receive until, and then receive up until the password bit. So if we do that again, now it just gives us our fake flag. And notice that on the first run we got it back twice, and on the second run we got it back 6 times. So because it's random, obviously there's a 1 in 256 chance of it coming back as a null byte, and that accounts for that variation. So now that we have that working locally, we can go and test it out on the remote server. So we go over to the remote server where I'm already in the correct directory here, so we were told that this is where we needed to go to test this remotely. And we've also copied over the Python script, so in our root directory we have secure login. It's exactly the same as the script that we were just testing locally, apart from the fact that the exe location has been updated. So we can now run Python and give it that file location. It might take a little bit longer to retrieve the flag on the server. Okay, it didn't take too long, and you can see that we're getting our flag back there as well. So that has been the secure login challenge. Let's go and check out some of the others. Our second challenge is called Tranquil, and we don't have too much information here in terms of a description. It says finally inner piece master ugwe, and we have a link to the binary, to the C source file, and then the server that we want to connect to once we get it working locally. So I've already downloaded all of these files. Let's go over to our local directory, see what we have. So we've got our source file, but before we have a look at the code, let's do some basic file checks. We can check the file type of Tranquil and see that it's a 64-bit LSB executable. As with the previous challenge, it's not stripped, but we have access to the source code, so that's not really too important. Let's run checksec as well. And we'll see that there are no stack canaries this time, so that's a hint that we're probably going to need to overflow the buffer. However, NX is enabled, so it's unlikely that our goal will be to try and get some shellcode executed, so it's more likely we'll be looking at some ROP gadgets or maybe a simple return to win style challenge. We could run the program. Let's run Tranquil, and we'll see it asks us for a secret word. We enter in a word, we get login failed. We could try that a few times and give some longer inputs to see if we can actually get a segmentation fault. In fact, let me do that now. You'll see we've got a segmentation fault, so there's a buffer overflow there. Let's go and try and find out where it is. Let's actually first of all as well, let's run ltrace on that and see. So it asks for a secret word, it's calling gets. Let's say ABC. And we can actually see that it's doing string compare with password 123. So if we run that again and enter password 123, we get logged in. The flag is somewhere. The flag is somewhere else though. So we're able to actually get the password there. But let's go and have a look at the source code and see where the buffer overflow is. So we'll open up tranquil.c. And here we have our main method. We can see it calls vuln, and there's another function here which is actually commented out called win, and we can see this function up here which prints the flag. So if we have a look at the vuln function, it declares a char buffer of 64 characters, and it asks us to enter a secret word which is going to be retrieved into this char buffer. But notice that it uses the insecure gets call, so rather than using fgets, which allows you to specify how many bytes you'd like to read in, this is just going to allow us to define how many bytes we want to write. So if we were to go and have a look at the manual for gets, we'd see that it says right here, never use this function, and we can go and have a look at the bugs below where it says never use gets, because it's impossible to tell without knowing the data in advance how many characters gets will read, and because gets will continue to store characters past the end of the buffer is extremely dangerous to use. It's been used to break computer security. Use fgets instead, and you can go and have a look at this to get more information about it. So we can see that there's a vulnerability there, and we know that we're going to need to write more than 64 bytes then before we're going to overflow the buffer and overwrite the return address. And essentially what happens here is whenever vuln is called, the address it's going to return to gets pushed onto the stack, and whenever we get to this return down here, it's going to return back to the function that called it, which will be our main function. So if we can overwrite the address that it intends to return to with an address of a different function, for example this win function, then we can get the flag in this case. So this win function, there's no path to execution, right? Without a buffer overflow here, there's no way that a user can interact with the program and have this function be called. So let's go and try and identify exactly what the offset is. We could try and do this just manually fuzzing, 64 characters and above to see how it goes, but it'll be easier for us to do that in GDB. So I'm going to open up gdb-pwndbg and pass in the file tranquil. In here we could have a look at the functions. We can see that we've got our win function right here, and that's where we're going to want to jump to. We can generate a cyclic pattern then. So we'll generate a cyclic pattern of 100. At the end of the day, we don't need to write too many bytes. We know that we're going to need to overwrite 64 to get to our return address, but there's no shellcode or anything to inject onto the stack. So all we really need is to identify where the buffer overflow is, and then we'll need 4 bytes on top of that to write our address. So we've generated our cyclic pattern. We take a copy of it, we'll run the program, and we'll paste that in. The program crashes as we would expect, and we need to have a look at the beginning of the RSP here to see what bytes were in it, what part of that cyclic pattern, and to identify the offset we can do cyclic-L and paste that in and see that it was 72 bytes in. So we need to write 72 bytes before we'll be able to overwrite the return address. You can see here it was going to return, and we want to return to the address of the win function, so we can actually just do here pwin, and that'll give us the address right there as well. So to help visualize this and make sure everything's set up correctly, you might want to create a fake payload here. So we can do python-c and then print out. In this case I'll do a times 72, which is going to be how many bytes we want to write before we'll be overwriting the return address. And then we'll add on to that our b's, so I'll say b times 6. And then we'll follow that by some c's, which aren't needed in this case, but that would in some cases be our shellcode, so I'll put say 30 c's after that. And we can print that out, copy this over, and then just run the program again in GDB and paste that in. And this just allows us to visualize this a bit better, so we can see all of our A's leading up to our RSP, and then we have our 6 B's from the beginning of the RSP. So everything is looking good there, and then everything else on the stack would be our C's. But for us, we also want to go to the win function. So the win function, let me take a copy of this. If we go back to our Python payload generation here, what we could say is instead of doing b times 6, we can put in this value in hex. So if we do plus \x, we need to do this in reverse order. So we'll do \x 96, \x 11, \x 40. This is just because it's in little endian format, so we're reversing the order of the bytes. And if we print that, we don't get a recognizable payload here, so we need to print this to a file. So I'm just going to pipe that to payload, and then if we run this again, if we run this and pipe in our payload, you'll see that we've actually got our fake flag. So in this directory I already have a flag.txt, which is just a fake flag that's set up, and that worked for us okay. So we can also try and run tranquil and just send in the payload, and that also works. So we get a login failed, but it is correctly jumping to the fake flag. We could go ahead as well and try to set up a breakpoint in this. So if we wanted to, let's disassemble main. We can see our main function here. Let's actually disassemble vuln, and the vuln function returns right here. So we might want to set up a breakpoint on that function, and then we might want to run it with the payload. and you'll see it runs through. It's actually stopped at a breakpoint, and you can see that instead of returning to where it should be returning, it's going to be returning to this 401196 win function. If we hit next, we'll see, yep, that's exactly where it jumps to. We can continue it, and then we'll get our flag here as well. So the way we just identified the correct offset and set this up, we actually don't need to do any of that in GDB or elsewhere. We can set up a Pwn tool script to automate that process for us. Now I've already set up a Pwn tool script to do this, so let me just open it up. exploit.py, and this is the same template that I normally use on these scripts, so all of this stuff up here just stays the same from challenge to challenge. I did slightly change this find instruction pointer function. So the first thing that we do here, if we can just even comment all of this out, the first thing we do is try and find out the offset. We know the offset was 72, so we could just type in here 72, but we can also use this function to find it. So this will launch the process, and it'll wait until, let's run the program again, it'll wait until it sees this colon, and once it sees a colon, it'll send a cyclic pattern of 100 bytes. It's then going to wait for the program to crash, and then we're going to check the offset. So you can see I've commented out the 32-bit code, which would have read from the program counter, which, notice right here, whenever we overflowed the buffer here, where's the A's? Okay, so whenever we overflow the buffers, the A's don't make their way into the RIP because they're not a valid address, but on the 32-bit system they would, so we would read the cyclic bytes from the program counter rather than from the stack pointer. But in this case we read it from the stack pointer, and let's try and run this and make sure it's working okay. If we run Python exploit, you can see I have the debugging on, so there's quite a lot of information there. We don't need to worry about it too much, but essentially it's showing us this is where the fault was, and this is the values in hex, and it's basically just searched in the cyclic pattern to find out whereabouts in the cyclic pattern were these bytes, and it's found that they were at 72. So with that done, we've got our offset, we can launch the program, and here we want to say our payload is going to be 72 bytes of a cyclic pattern, so we have our offset here, and then at that offset we want to write the address of the win function. So we could just go and, let's go back here and do pwin. We could just take a copy of this and paste this in here. That's absolutely fine as well, but because we've actually loaded the executable file in here, we can just read the functions that are available to us. So I've chosen to go for that route instead. We then write the payload to a file so we can reuse it, send it to the server and stuff like that, and then we just wait until we get that message to say the login's failed, and then we take our flag. So if you try and run that now, let me clear this, Python exploit, you'll see it sends all that off, it comes back and retrieves our flag for us. And the cool thing about this template that we use there is we can just pass in GDB or remote as an argument, and we can set up our GDB breakpoints and stuff here as well, and that means we don't actually have to go and start changing the script depending on whether we want to debug it or whether we want to test it remotely. So if I just go and grab this server and port number, and then we run the exact same thing again, Python exploit, but type in remote and then just paste in the server and the port and hit enter, and that does everything for us. We get our flag, time has gone too fast without watching the leaves fall from our instruction pointer, and there's our flag. We could have also used a ROP object here as well to call this, but I'll not bother in this case. Okay, and let's move on to the next challenge. The next challenge is called Sanity Checks, and as usual we have a program and the source code here as well. It says, on the off chance that someone does get in, I've added some sanity checks to detect if something fishy is going on, see if you can hack me. So we again want to test this out locally, and then we'll be able to try it against the server. So I've already got the files downloaded into our local directory. So if we list the files in the directory, we have our fake flag for testing, we've got our source code, we have the binary so we can check the file type, and as usual it's a 64-bit LSB executable, it's not stripped. If we go and have a look with checksec at the file protections, we'll see that there's no stack canary, so again good chance there'll be a buffer overflow in this case, but it doesn't look like we'll be trying to get any shellcode on the stack to execute because the NX enabled flag is set. and there is no pi. So we could run the program again, run checks, it's asking for secret word, we can just enter something in, login failed. Okay, so we could try that again with ltrace. Ask for the secret word, we could enter something in. We can see there it's actually compared it with password 123. So if we run that again, and this time we'll enter password 123, and it says logged in, let's just do some quick checks to make sure everything's in order. And it says nope, something seems off, something seems off. So we could run that again just without ltrace, and you'll see that the output a little bit more clearly. But let's go and have a look at the source code and see what's going on. So we'll open up checks.c. So we've only got one function here, the main function, so it's not like our return to win style challenge where we had to jump to another function. In this case, so we do still have the password of 64 bytes, and it's reading that in with gets, the dangerous function, which is not going to check to make sure this is going to fit within the buffer. So we will be able to overflow the buffer. We need to make sure as well that the password equals password 123 in order to pass this check, and then we have some other checks that need to pass as well. So these variables declared here, the naming doesn't seem to make much sense. They're all set to 0, and then after the password's been verified, it'll go through and check each one of these variables and make sure they equal certain decimal values, which obviously they shouldn't equal because they've been assigned as 0, and at no point have we been given any option to change that. There's no code anywhere here that's assigning them new values. So unlike the previous challenges we've looked at, in this case our goal is going to be to actually write over these variables with the values that we need in here. So we can play around with the offset and find that if we enter in our password and then enough bytes to overwrite this 64-byte buffer, we'll start to actually eat into these variables which are on the stack, and we can overwrite those with the values that we need. So let's open up gdb-pwndbg checks, and there's only our main function here, but we can check info functions to get a list, and then in this case we want to disassemble the main function, and there are some different instructions here we might want to set breakpoints at. So we have our string compare where we compare the password, so let's set up a breakpoint there, and then we have our comparisons here as well with the different values. So 32 in hex is 50, so that's our first check, and then we have 55 is going to be compared to 37 in hex. So we might want to set some breakpoints up here as well. Let's just set up a breakpoint at the first one. Once we get the first one working, then we can set up breakpoints at the others if we need to check the alignment. Let's do B star, set that breakpoint up, and essentially we'll be, as we're building up our exploit in our payload in Pwn tools, we'll be able to go and set a breakpoint here and find out what does RBP minus 4 actually equal, and depending on what values in there based on what our payload is, we'll be able to adjust our offset until it actually aligns, so that if we inject a value of 50 in decimal, we want to make sure that it's being injected into RBP minus 0x4. So we could run this. Let's generate a cyclic pattern as we usually do to identify the offset, but in this case obviously we're not looking to overwrite the return address. But if we run that and paste that in, we hit our breakpoint, but obviously this is the comparison with the password, so if we hit continue it's going to fail to log in because we didn't have password 123 in there. So that's fine. We'll just need to, whenever we run it, we'll need to put in password 123 before we put in our cyclic pattern, and we'll need to account for that then with our cyclic pattern as well. So now if we go to search for whatever's made it into the RSP, let's hit continue, we have AAAY, so we can do cyclic-L, and that was 93 bytes into our pattern, but obviously then we also had our password 123 as well, so that needs to be taken into consideration. But I just wanted to go and quickly demo that in Pwn tools, in gdb-pwndbg. We'll actually move over to our Pwn tools script now, so open up exploit.py. I've already put this together, so I'll just, rather than go and type in all the code out on video, I'll go through and explain what's going on. Okay, so as usual we're using our Pwn tools template here. It's set up to grab the context, and we don't need to worry then about the architecture and how many bits and stuff to use for addresses throughout it. It'll take care of that for us. We have our find instruction pointer, but in this case obviously that's not exactly the offset that we're looking for, but we've set that up anyway, and we send in the password 123 and our cyclic pattern as well, and then we just adjust the offset based on the length of our password. So that'll come back with the offset, and then we want to send off our payload. Our payload is going to be the password again, because we need to match that first check in order to get into this into these if statements. And then we're going to put in our values. So we have 0x11 there, which is these are in reverse order here. So we have our 32, our 37, our F5, and I kind of played around with this just with in this case we're minus 16 from the offset in order to account for these, and I just kind of played around with this value. So you'll see I set up some breakpoints here, the first one being, I think this is actually our two comparisons there. So let's try and run it with GDB. If I go back and we also write the payload to a file here. So if we do Python exploit gdb, let's move this window over here, and it stops at its first breakpoint. So if we hit enter, let me actually minimize this so you can see it a little better, and we stop off at this comparison. So this is our first comparison. We're comparing 32 in hex to whatever's in RBP minus 4. So in that case we would have a look and see what does RBP minus 4 actually equal. In this case it does equal 32, because I've been through and checked this. I went through and made sure these were all in alignment. So whenever this wasn't matching, what I would do instead is print out x over 20x, and let's say minus 16, and then try and work out where is our value. In this case you can see it's right here, so you would just go and add 4 bytes at a time until you work out what the right offset is. And then after that it's going to go on to the next check, which is going to be 32, and that's going to be checking RBP minus 8. So you can see that's at 37 I mean, not 32. And then similarly we'll do the same with our minus 12 is going to be F5, and then again 16 is going to be our 3D, and then finally 11 at 20, minus 20. So it'll go through all those checks. If I hit continue here, it's going to stop off at that next breakpoint as well, I believe, and you could just go and make sure everything's still in place. I know in this case that it is going to be, and if we just hit continue, it'll print out our flag. So I think that's basically everything that needs to be mentioned here. Now, in order to test this on the remote server, all we have to do is run the same script with the server address and port number. So I can just take a copy of this, and then we can run Python exploit remote and just paste in the server address and the port number, and that'll get us our flag. And that's been the Sanity Checks challenge. So let's move on to the next one. The next challenge is called Sticky Stacks, and again we have the program, we have the source code, and we have the server to connect to, and we're told that there's a lot of secrets, maybe even a flag. So we've already got the files downloaded here. We can see that we've got the sticky stacks, so let's check the file type. And again, 64-bit LSB executable, it's not stripped. If we check the security settings, we'll see that there are no stack canaries. NX is enabled, so if there is a buffer overflow, we won't be able to execute any code that we inject onto the stack. Pi is disabled once again. So let's run the program, see what it does. So it asks us for a name, and then it just repeats that back to us. You can see here it's not actually repeated the full thing back to us either. So there's only one opportunity for input, and there's no buffer overflow here. So let's go and have a look at the source code before we do anything else. So we have this secrets struct, which is declared here, containing a variety of char buffers, including the flag, which is what we're interested in retrieving. Whenever the program launches, it's just going to call vuln, and vuln is going to set this 7-byte name variable, which is what we saw whenever we put in crypto. It only repeated crypt back. And then it's going to create a secrets struct object and assign some values to some of these items in it. And it'll open up the flag.txt, and it'll also it'll read in 128 bytes into the struct. It's then going to ask us for our name. It's going to read in 6 bytes, so there's no issue with the buffer overflow there, as we saw. But it's then going to print out welcome and then just printf the name that we provide. So this is a clear format string vulnerability, because the developer hasn't specified what type of input we're providing. They should have specified that they're expecting to receive a string, and therefore whatever we enter should be interpreted as a string. Because they haven't done that, they've allowed us to do that for them. So if we go back here and run the program and put in here %s, there we've got welcome welcome. Let's do that again, and we'll do %s, and we've got welcome null. We could do that again. See if we might not be able to fit 3 though. Okay, so and this is essentially reading items off the stack. So we could do that again and try and represent this as hex. Again, we can do %x, but because we don't have much room to write here, we can't keep looping through and going through all the items on the stack, so we need to use a different notation to do that. And to do that, we can say here percentage and then give a number, let's say element 13, and then dollar. So we're saying we want to print out the 13th element on the stack, and we want to represent it, in this case I'll say as hexadecimal, and then that'll return. So we could do that again, and we can do this if we're doing this with the string. What we need to be aware of as well, you see we got a segmentation fault there. So when we try to print as a string, we're not actually trying to print the item on the stack as a string, we're trying to print the item which is pointed to as a string. So if we have on the stack 4 A's, for example, that would be 414141 in hex, and we would be trying to print whatever is at that memory location as a string, which obviously is an invalid memory address. So in a case like this, we get the segmentation fault. So in that sort of case, we would actually want to print it as hex, as we've done here, and then we could simply take this and decode it in Python or on CyberChef or ASCII to hex.com and find out what it actually equals in text. So we're going to want to try and loop through the items on the stack, print them out, and see if we can start printing out some of this information and hopefully get to the flag. So again, we've got a local fake flag set up to test this out, and I've already got a script prepared as well, so let's open this up. So I already have this set up with the correct values, but initially to solve this I just looped through like 1 to 100, and we're printing these out as pointers. We could print out as hex, but it's not going to give us this full 64-bit that we'll need. So if we run this, you'll see that it's actually going to crash because I'm trying to convert these all into hex, and that's not going to work for us. So first of all, we'll just want to comment some of this out and just print out the result. And then we can change this to warning so we're not getting so much noise. And if we run through that, we're printing out all the values, and essentially we can go and try and look for something that looks like a string, or we could go to ASCII to hex.com. So if we go and let's do cat out the flag, so we've just got here our fake flag. And if we were to go and convert this, you can get an idea of the string that we're looking for. So let's go back, and we're looking for a 66, a 6C, which it looks like we're going to have around here. Bearing in mind the ordering may be different, but we can then take this, let's take this actually and convert this back on ASCII to hex. And you can see there, so we've got the flag, but it's reversed, or we've got the first half of the flag. So essentially this code here, all we're doing is we're we're converting this into hex, and then we're also reversing it as well and appending it to the flag, which will be printed out at the end. So whereabouts was the flag there? It was at, oh, we're not printing out the number. I believe it's around like 31. Let's print 31 to 35. Yep, 31. So if we do 31 to 33 and try to convert it into hex, you can see that it's got back our flag this time. It didn't give us our success flag at the end, though, because we've turned off the login. So if we put that back to info, run that again, this time we'll get our fake flag at the end. So then we just need to do the same thing against the server. I'll revert this back to what we had, because it was 33 to 43 because the flag's a lot longer. But if we now just use the exact same script, and we'll go and take the server and port, and then we can run this again with remote, paste that in, and that's going to come back. You can see it's getting each segment of the flag, and then at the end it's going to reverse those all and append them together, and then we get our flag. And that's been the Sticky Stacks challenge. So we might check out some more of these challenges. I'm going to move on and have a look at some of the reverse engineering and web challenges as well.